Okay, everybody, welcome to Tuesday and today's presentation. We have a special one today from Uponor, and it's about the basics of radiant heating and cooling. Such a system promises to provide exceptional comfort, energy efficiency, and indoor environmental quality. To tell us all about it, please meet Robert Bean.
Good day, everybody, and thanks for having me on. And we've got a full 45 to 60 minutes ahead of us, and we're going to be talking about a whole bunch of different things. Before we get into it, just want to share that that's my ugly mug there on the on the screen now, and it's been a real treat for myself in the business of indoor environmental quality, and particularly its role with radiant heating. And I've been doing this now for, I don't want to share it because that'll date me, but about 34 years. And I've really sort of seen, really I've been up the technology ladder and down again, and I've seen a lot of things from very, very small projects to very, very large projects all over the world that is using this technology. So today's discussion is we're going to start off really sort of just talking about some of the features and the benefits about sustainable HVAC systems, and particularly as they relate to buildings. I'm going to sort of set the stage with some bullet points, and then I'm going to very shortly spend some time talking about the history of radiant. It certainly is not new, and doesn't have to be expensive, and it can be simple. And we're going to give you some examples of that towards the end of the presentation. We're also going to talk about radiant energy, particularly as it relates to buildings and long wave and short wave radiation on a building and how that influences the internal environment. And we'll bring up discussions on thermal bridging, and we'll talk about mean radiant temperature and some of these terms that are finding their way more into the building sciences and the science of thermal comfort. And then we're going to talk about one of my favorite topics, which has to do with sustainability and energy, and not only in terms of conserving the quantity of energy, but also conserving the quality of energy. And in terms of the topic of sustainability, so much of the world is focusing on reducing consumption, which is a quantity element, but we forget about the quality of the energy that's used and how that really is what we should be paying attention to when it comes to sustainability. So that'll be a very interesting part of the discussion for those of you that aren't familiar with terms like exergy efficiency, not energy efficiency, but exergy efficiency, and we'll briefly discuss that. And then we're going to get into talking about thermal comfort. And it's an interesting area because by and large, most people in industry aren't aware that there are in fact thermal comfort standards. And within these standards, there's a large discussion about the role that radiant energy plays on the occupants. And so we're going to describe those elements. And in order to understand the relationship that people have with the built environment, we need to understand, at least on a basic level, how human beings experience comfort from a physiological perspective. So we're going to talk about that. We're going to show you some photographs of some research chambers that are used to study thermal comfort, and that'll be kind of a fun part of the presentation for today. And then we're going to jump into looking at different sustainable energy sources and comparing that to our traditional or typical sources that we use today, and we'll explain how that plays a role in these low temperature heating and high temperature cooling systems and how that sort of fits into the world of sustainability. We're going to talk about some of the training programs that contractors across the country are taking to really start to understand how sustainability fits into the world of construction, particularly how radiant fits into that picture. So we'll sort of describe a few of those pieces of the puzzles. And then for anybody that's online today that maybe has a background in inspections and codes and standards, I'm going to share with you some of the things that we're doing up here in Canada because we've taken great steps to bring design requirements and installation requirements into our national building codes. And of course, that is then enforced all the way down to the municipal level, coast to coast. And it may be a model our brothers and sisters to the United States could also possibly adapt. And then we'll finish off to the presentation showing some photographs of some really simple radiant systems that can go into any house of any size, and how elegant these systems can be, not only from a installation point, but also from an operation, and how that benefits the occupants and meets requirements for sustainability. So let's get into the discussion.
Well, but Robert,
We
before
have,
we
like I
do
said,
that, Robert,
yes, sir,
before
go
we
ahead.
do that, I want to make sure that people understand your background on the topic, because you have quite a background on this. Um, so if I could just take a minute just to introduce you to the group.
Sure.
See, Robert is a registered engineering technologist in building construction through the Association of Science and Engineering Technology Professionals of Alberta, Canada. He's also a professional licensee in HVAC through the Association of Professional Engineers and Geoscientists of Alberta, and he's president of the Indoor Climate Consulting Incorporated and technical director for healthyheating.com. So Robert has quite a background on the topic at hand. I did want to remind our audience that if you have questions for Robert today at any point, please submit them in the small box at the bottom of the Q&A, and then we'll pose those questions to Robert during the Q&A time that we've set aside near the end of the webcast. Sorry to interrupt there, Robert. I just wanted to make sure that people knew that, and please, we're all ears now.
Okay, thanks very much for that, Mike. Appreciate it. All right, so let's start off with certainly the world of architecture and the building sciences recognizes the role that radiant systems play. And as you'll find from at the end of this presentation, that what we're talking about is using really low temperatures for heating and high temperatures for cooling. And although this presentation is predominantly for heating systems, during the Q&A, if you have any questions on cooling, I would certainly be willing to answer those for you. So in terms of sustainable hybrid radiant-based systems, these are sort of the elements that I focus on in our design practice. And first and foremost, when we talk to clients, is we want to bring their awareness that HVAC really sort of begins with the building enclosure, and we're going to show that in a little bit more detail in a couple of upcoming slides. But at the end of the day, all of the experience that we have thermally with a structure starts with that enclosure. It's sort of the interface between ourselves and the outdoor environment. But the building enclosures aren't perfect, and neither are our bodies. We do have some capability of adapting to indoor and outdoor spaces, but again, we're not perfect. So we'd still need to augment the flaws, if you will, in the enclosures with some type of an HVAC system. And we use radiant in our practice simply because we can get down to really low temperatures, which really improves the combustion efficiency or the COPs of heat pumps. And it also lends itself really well to renewable sources. One of the things that we like about these systems is that radiant component takes care of all of the sensible loads in a space, anything that has to do with energy transfer in the absence of moisture. And by doing that, we can then have an independent ventilation system, which is dedicated to bringing outdoor air and then conditioning that outdoor air for the purposes of providing healthy indoor air quality. And of course, if we can influence the health of the environment, then we can have an influence by connection to the occupants. And the nice thing about these hybrid systems is that there's no confusion. The heating system isn't confused about having to do dehumidification or humidification at the same time that it's doing space heating or cooling. We have a system that's dedicated strictly to the thermal comfort component of the occupant, and then another system that's dedicated to the respiratory comfort. And this is, in fact, how our biological systems work from a physiological point of view, as we'll explain earlier on, later on, and then it also reflects actually in codes and standards. And so we'll talk about ASHRAE 62.2 briefly, and then also ASHRAE Standard 55, which is the thermal comfort system. So let's then look at some of the things that we shoot for. As designers, we are looking for low temperatures, and so what you should notice here that when we talk about fluid temperatures and heating systems of less than 80 degrees Fahrenheit, we're talking about temperatures lower than what you find on the human body. So we're talking about heating people with temperatures cooler than your blood. And we'll point that out later on about how important that is in terms of the world of sustainability. And then same thing on cooling, very high temperatures. Instead of using 40 degrees Fahrenheit or 45 or 50, we're really looking for really high return temperatures. And this, of course, really improves the COP performance in cooling equipment. And then the next line down is really important, and that is we always try to strive to match up the source temperature with our load temperature. So if we need 85 or 95 degree fluid temperatures for heating, where can we find that kind of temperature without generating some other higher temperature, which then, of course, is a waste of the quality. As I mentioned earlier, we'll talk about this quality of energy. So very, very important. And then the other benefits that we find with these radiant systems is that we can use flooring that traditionally people would avoid because of the feeling of being cold. And, we hear this a lot, cold tile, cold concrete, whatever the floor is. If it's a masonry type floor, because of its really high conductivity, it has a capability of drawing energy out of the body at a much higher rate than more of the sort of fabric type floors or plastic flooring. So the masonry floors, the beautiful thing about them, is they do have a low VOC component, and so if we can use them, then we improve the environment from an air quality point of view, and if we can condition them, we can improve them from a thermal comfort. We also want to point out that we want to use high densities of tubing, and as we'll see later on, that has an immediate effect on the operating temperatures of the heating and cooling plant. So if we use wide temperatures, we end up with having to use hotter fluids. If we use narrower temperature spacing or tube spacing, then we can use a lower temperature. And then just some other elements there that we'll talk about. So let's do the history part and just point out that it's a very old system. I'm going to show you some photographs that are from ancient times gone by, which are very, very cool, and we'll get to those. They're also very simple systems that are being used today. And one of the things we certainly find out is that as building performance is going up, these mechanical systems can become more simple. They don't need to be complex, and they certainly don't need to be expensive. All right, then let's look at this next slide. And so what should be coming up on your screen is a photograph of the world with some dates placed on top of it. And if we had more time today, we could explain all of the sort of the milestones in the development of radiant heating and cooling systems. But you should know that almost 3,000 years ago, inhabitants of what is sort of modern-day Korea and the Aleutian Islands up in Alaska have used these very old radiant systems. And one thing I do want to point out is that back in around 700 AD, there's actually a reference in literature to radiant cooling systems. So radiant heating is not, or cooling for that matter, is not new by any stretch of the imagination. And there's some significant things that has happened over the years in its development, particularly towards the end of World War II and also in the 70s. But anyways, we won't have time to get into that, but just to know that it's a worldwide growth, and it's a very interesting study in anthropology and architecture. So what should be coming up on your slide next is slide number 8, and what we're looking at is Alaska and the Aleutian Islands, and there's an archaeological dig going on there right now that have uncovered this really old type of radiant heating system that was used. And it's interesting because this method was also used in Korea, North Korea, and I'm just going to go to the next slide there, and you can see sort of a larger screen. And so if you can imagine what's happening is they would excavate the earth, and they would then have a fire at one end of this excavation and then a flue on the other end, and then they would put rocks or stones or whatever they could find over top of this makeshift flue, and they would then draft the heat from the flame under these stones, and of course that would then heat the stones and then radiate into the space. And this style of heating we find all over the world, and this eventually led to sort of in terms of modern day, in terms of the Greeks and the Romans, the ondol systems, and or hypocausts, and then of course it just grew from there. So very interesting history as it relates to radiant. So let's look at what's happening in architecture and building systems, and how that's going to play a role further down in the future in terms of HVAC systems. So we certainly have seen a shift. When I got out of school in 1983, back then in Canada, we had our R2000 programs, and there was high-performance buildings, and we really started to see the introduction of air-to-air heat exchangers or energy recovery ventilators, which, by the way, ERVs actually were on the continent before HRVs, and that may be a surprise to some, but there was actually a company in Germany that was exporting the units. In 1979, there was a patent pulled for the first ERV that was distributed in North America. So a little bit of trivia there. Anyways, we've seen this shift from what I call the terrible building construction. Quality was good, but they leaked like a sieve and had very high energy bills, or energy consumption, I should say. And we've been moving from the terrible into the traditional, and then now we're sort of in this what I call transitional state, moving more towards terrific codes, where we're slowly seeing a reduction in what I call the flux, which is the BTUs per hour per square foot. We're certainly tightening up buildings. We've moved from a 6 ACH 50 now to where we're starting to see 2 and even lower when you look at passive housing standards. And as a result, we're starting to see a reduction in the temperature requirements for heating up these spaces. All right, on your screen now is a modification of a graphic that comes out of one of the ASHRAE Advanced Energy Design Guides. And what I want to use it for is just to illustrate what actually happens to a building, because it really has 3 functions. It serves as a filter and a sponge and a capacitor. And what do I mean by that? I mean that when you have differentials in temperature, pressure, and moisture, the flow will always go from high to low. So if we're talking about air pressures, for example, if the pressure outside of the building is higher than the pressure inside the building, then the flow will go from outside to in. And whatever is in that airflow, in terms of particulate and gases, these types of things, will come through the enclosure. So the enclosure acts as a filter in this aspect. And the same thing with moisture. If we see moisture levels, higher vapor pressures outside than we do inside, then of course that flow will travel again outside to inside. And so the building becomes a sponge, and then also in terms of a capacitor for heat. So that heat, which is what we're talking about today, of course the source energy is the sun, and it delivers to the earth shortwave radiation. And that radiation then is either absorbed into the solid components of the structure, so that being the outside enclosure, and also through the glazing system, through the fenestration. So we have shortwave energy penetrating the building that raises the inside temperature of the space, but we also have the shortwave landing on the building, and that of course then gets conducted through the space as a long wave on the inside surface towards the interior in a long wave format. So we have both shortwave and long wave energy inside the space, and we also not only can gain energy that way, or heat, as it's converted to heat, but we also lose energy in the same format. As it relates to people in spaces, that is always at a long wave format as opposed to a short wave. So it's a very dynamic set of conditions that are always playing between the moisture and heat and energy and whatever is flowing inside to outside or outside to inside. Of course, that building is there to serve as a filter, sponge, and a capacitor. And our job as indoor environmental engineers is to sort of control that indoor environment, recognizing that these elements are taking place. So next on your screen is 3 photographs using thermography, and what I like about this slide is it really illustrates a couple of different things. The first one is on the left-hand side. You can see the door and the cool environment that surrounds that door. And then in the second picture, you can also then see the thermal bridging that occurs as a result of the wood framing members there. And you can also see areas of thermal flaws, if you will, in the corner, the intersection between the walls and the floor. And then in the third picture, you can then see the effect of having a cool window and also the thermal bridging. So you can imagine being in that space in the middle of winter, and as warm bodies, energy will flow to these cooler surfaces via the radiant process. And it's the energy leaving our body via radiation that gives us the cooling sensation. Oftentimes we talk about buildings being cold, but in fact it's not that the building's cold, it's that we as occupants are cold. And so that is a really important element to focus on, is that as designers that we remind ourselves that we're doing what we do for the sake of the occupant and not the sake of the building. All right. So what's on your screen next is an FEA study. That's the finite element analysis that we've done on building components. And we did this particular one because we wanted to see what the influence would be on the interior surface temperature of a space using 2x4 or 2x6 construction, and then changing the exterior insulation component from 0 insulation to all the way up to 4 inches. And you can see, and this is in Celsius, but I'll just point it out in Fahrenheit, that as we go, if we take the bottom set of models, if we start with a 2x6 wood frame with no insulation on it, and move our way right to left, where we get to the very end, you can see that there's a big difference on the interior surface of the space by having that 4 inches of rigid insulation there. So what that means is that during loading, in the heating mode, as the interior surface of the building warms up, there's a less differential between our warm bodies and these surfaces. And because there's a less differential, as the occupants, we retain more of our heat as opposed to losing the heat to the enclosure. And that's the effect of having these high-performance enclosures, is that it allows the body to actually retain its heat as opposed to giving it up and then having to experience this discomfort from the cooling process. And you can see this, the difference between high-performance buildings and low-performance buildings using, again, the thermography. And here we are showing a high-performance building on the right and a low-performance building on the left. And this is simply just a function of the enclosure itself. So let's set that aside, and let's move into the next topic, which has to do with energy quantity versus energy quality and the conservation of both of those. And it's an area that I think we'll see more as time comes on. So I'm going to go through a series of slides here, just pointing out inappropriate things that people have a sense of, and then showing how our sense of energy appropriateness doesn't actually exist in the world of architecture. So, for example, we would never use a backhoe to plant flowers. It's an inappropriate use of energy for a low energy process. Likewise, with hammering finishing nails, and we would never use a sledgehammer to pound in a finishing nail. We would use a more appropriate tool for that. And same thing with mowing lawns, although some of my neighbors have lawns that they could probably use a combine on it. But again, we have tools to do the job that are more appropriate. And likewise, when you see someone out watering the lawn, it would be inappropriate for this fireman to show up to water your flower bed when you could do a much lower energy system. And we have a sense of energy frustration when you get in behind something like this vehicle here. And we've all experienced this, that you just want to get away from this guy, but because you're being frustrated by that the lack of speed. And likewise, you have this sense of energy exhilaration. If these two characters were on our roadways, some of us would probably like to follow them along, but this kind of sense of exhilaration exists. So as a society, we actually have an intuitive sense of what's appropriate when it comes to energy. The exception is when it comes to architecture. And I'm going to show one of the buildings in Chicago to illustrate this point. This is the Aqua Tower, and some of you may be familiar with it. We covered it actually in one of our stories, I think it was last year. And I was fortunate to be in Chicago many times during the construction of this building. I wasn't involved in it. I'm happy to say that. But there's many accolades given to this structure, and people who don't understand building science and comfort and these types of things look at structures like this in awe. But when you look at the building from an energy perspective, you really get to see the flaws. And this is an excellent example of thermal bridging, cooling fins really on a structure. And this is the type of things that we need to teach people as it relates to energy and energy use. Now, this is a Sankey drawing, This is for the United States, but in Canada we have the exact same problem, and that is that roughly 50% of the energy or let's just say that half of the energy is lost in the process of converting energy into one form or another. And the reality is that no matter what we have in terms of using energy efficient equipment, it doesn't fit into the model of sustainability if we have to generate 2 units just to use one and the other one we throw away. It's just insane how we allow this type of stuff to go on. And so that energy waste is lost in terms of heat, vibration, sound, all of these sort of parasitic loads on our energy systems. And so we say that when energy is converted, entropy is created, which is what you see in the cooling towers. They're the thermal part of it. But what's not seen in these illustrations is this concept of exergy, and we're going to get into that. So we conserve the energy quantity by using high-efficiency equipment, but even in the process of using high-efficiency equipment, particularly the combustion stuff, we're still generating very high temperatures. In fact, combustion ranges anywhere between, say, 31 to 3,200 degrees Fahrenheit. And so I don't know about you, but for me, if I see 3,200 degrees Fahrenheit and we only need maybe 99 or 100 degrees to maintain spaces, there's this huge disconnect between what we're using and what we're generating. And this is what we call very poor exergy efficiency. And in fact, something that has, say, 97% combustion efficiency, in reality, from an exergy point of view, may only have 3% exergy efficiency because we've destroyed all of those useful temperatures in the process of conserving less. So if you look at long-term prognosis for energy over time, and we could say that our supply, if we simplify the illustration, is certainly being reduced. I don't think anybody has any misunderstanding about that. Our renewable or non-renewables are a fixed resource, and but what's happening in the world of architecture is that we're using these oils and gases and coals to heat our spaces, and our spaces can be conditioned with really low temperatures. We don't need to use high temperatures, which is a result of turning these the hydrocarbons into high temperatures. So over time, we're seeing a reduction in these hydrocarbons, which we could be using for industrial purposes, and instead we're using them for architectural purposes, and that is completely a big flaw in the world of sustainability. We simply can't say it's enough to conserve the quantity of the energy while in the process of destroying the quality of the energy for non-industrial use. So we have some road work there ahead of us to teach people about this. So to understand quality for thermal comfort, we need to understand the science of the health sciences and how that relates to thermal comfort and indoor environmental quality. And in terms of IEQ, of course, it's more than just air quality. It's actually all of these elements that you're seeing on your screen, we should be on slide 33, Mike, if you're paying attention, if you're wondering. So it's all of these things together. Now today we're only going to be talking about thermal comfort, so let's look at the standard. And the standard is ASHRAE 55, Thermal Environmental Conditions for Human Occupancy. And when I travel all across the country, one of the things I ask in my courses and in my lectures is that how many people have this standard. And it's unfortunate, but I would say less than 3% of the population that are involved in construction actually know that the standard exists, and even less than that, probably about 1% actually own the standard, which is really unfortunate. So the standard is made up of a whole bunch of different elements. Today we're going to talk about radiant, which plays a huge component in it. And we can see that using thermography in terms of the people. And this illustration here really sort of hits home in that the temperatures that we need today in relationship to the bodies are actually at lower temperatures than the body in terms of the blood temperature and the skin temperatures. So very low elements. And in spaces, we actually exchange roughly 60% of our energy via radiation, which is surprising because most thermostats don't measure radiant, they measure air temperature. The study on radiant goes back a long time, and one of the key researchers was a medical doctor, Vernon, and he observed the discomfort that occurs in the space due to radiant cooling. So again, going back to this radiant temperature, or the surface temperatures in the space, which is defined by MRT, or mean radiant temperature, when it's cool, our body releases the energy to that space, and it's that process of the energy leaving that causes the cooling sensation. The next slide that comes up, on the left-hand side is a photograph of the Danish Technical University Environmental Research Chamber, and on the right-hand side is the one from Kansas State. And clearly, what you can tell from this research project is that half-naked women in Denmark are much happier than half-naked men at Kansas State University. But what the labs were used for was to find out where people are thermally comfortable in spaces depending on the environment. And it was from that research work that graphs like this came up, looking at temperature stratification in spaces as a function of the type of the heating systems. And what you find with heated floors is that you have a much more consistent temperature as opposed to the sort of the stratification effect when you get with other types of HVAC systems. And then we also studied with these laboratories and the effect that radiant has. And so when we normally look at spaces, we tend to think that they're homogeneous and that a single thermostat could represent the occupant. But in fact, they're dynamic spaces, and the sun moves across the building that changes the radiant profile inside the space. And so the use of air-based thermostats as an ambassador to the occupant is a real flaw that we have today when we should actually be measuring what's called operative temperature. And operative temperature is what's in the standards, and it integrates mean radiant and dry bulb. And then some of the other tools that we have are the Sherlin photography, which allows us to see thermal energy moving in a space, which is something we were never able to see before until this technology came up. So it really allows us to understand the energy flows or the heat flows. Of course, most people are familiar with these two tools when looking at buildings, but in the world of comfort, we actually use this type of an instrument. And this instrument represents all of the senses that we have, thermal senses that we have in a space, and of course what's in the ASHRAE 55 standard. So let's talk very quickly about thermal comfort and the role that our skin plays in spaces. And we can see the influence of heated and cooled surfaces on our body as the temperature of the skin goes up using PET scans. And so again, the modern technology allows us to see how the influence of the space has on physiology. And then if we had more time, I would love to spend a lot talking about this particular illustration, but you need to know that people have a process, and it's an internal process that senses comfort and is done through the nervous system, through the senses in your skin, but also is hormone-based. And so we have epinephrine and norepinephrine, and then T3 and T4. Those four hormones are what regulates body temperature. And the central place or the central operator is called the hypothalamus. And the hypothalamus really sort of tells or releases hormones, TRH, into the pituitary thermostat or the pituitary gland, and then it's connected to your thyroid gland. But anyways, it's a very interesting topic, but you need to know, again, as humans, we have our own ability to sense the environment, and that is through our skin and through the hormones in our body. And it's the regulation of these hormones using the feedback system or negative feedback system that regulates the blood flow. So whether we're either constricting blood veins and arteries, capillaries, or dilating them, it's that flow of blood to and from the skin that allows us to either heat up or cool down as required in the body. Now this study has gone into further depth using mannequins, and this is Adam. And Adam is used in the automobile industry, and if you stripped Adam down, what you would discover are the senses that the human body has. And we have roughly 160,000 some odd thermal sensors in our skin, and we use that to measure the environment from a thermal perspective. One of the interesting things about that is that those sensors are not located in a sort of homogeneous way around the body. They're actually located in higher densities in the exposed areas. So your hands, your head, and your feet. And so it's another fascinating area of study for thermal comfort. And whatever your beliefs are about why we exist, I think it's just fascinating that these sensors are located where they are in the proportions that they are, knowing that most human beings are exposed in these particular areas. So it travels, the thermal information travels from our skin sensors into our spinal cord, up into our head, and that's why that we say that real comfort is actually on the inside. In other words, we can talk about putting in comfortable furnaces and comfortable boilers all we like. At the end of the day, all these equipment do is they have to create the conditions necessary for the human to experience thermal comfort at both a conscious and an unconscious level. So coming back to sustainability and energy use, knowing that we've got this biological being, us, humans, made up of flesh and bones and nervous systems, and that we function with our own internal temperatures, starting at our skin, working our way into our core, that ranges anywhere between, say, 85, 87 degrees, something like that on the skin temperature, if you averaged all of them out, into that sort of that 98, 99 degree internal temperature. So very, very low temperatures. And yet we burn oil and gas and coal and all these other fuels to generate 3,200 degrees Fahrenheit. And it's absolutely insane that we do that. And so let's just flip through some of the alternatives that we could easily use that are more in tune with our needs. And geo, of course, is a perfect example. We have no combustion process, yet the temperatures with a geosystem is more than adequate for radiant heating or low temperature heating and high temperature cooling systems. Likewise, when you get into wind power, when you get into hydropower, also when you get into solar thermal systems, or if you get into the PV systems, all of these systems operate at or are able to generate power or heat at a temperature that's more aligned with the temperatures that we need for the human body. And then one of the other ones that's an interesting study has to do with evaporative night sky radiation, which is this photograph that you see up on your screen there now. So these are all systems that don't require combustion and they don't require compression, and they're far more aligned with the low temperatures that we can do with heating and high temperatures for cooling. So the training that's going on right now, we see contractors all across North America studying these aspects and using design tools like you see there up on your screen. And this actually comes out of the ASHRAE handbooks. This is a design graph that radiant designers use for designing these systems. And one of the things I want to point out is that through the manipulation of floor coverings, for example, and the building performance, we can see temperature ranges anywhere between 80 degrees Fahrenheit for a high-performance building using very low VOC masonry-type surfaces, or all the way up to 150 degrees for a very poor building, having to use, say, carpeted as our means of radiating energy into the space. So these are not trivial matters. When the radiant designer sits down with a builder, one of the objectives is to try to get the lowest temperature possible. And how we do that is working with the client to get the building load down, working with the interior designer to use, if you can, the lowest VOC materials, highly conductive, more than masonry type surfaces, and then using really tight tube spacing. And when we do that, we can drop the temperature down from 150 to 80 degrees, and that just has benefits all the way through the system. So I mentioned we were going to talk about codes and standards. We have about 5 minutes left here, and I just want to show you what we're doing in Canada. We actually have a code for hydronic systems. It's called CSA B214. And I'm not going to go through all of the items there on your screen, but it's enough to know that this code has been adopted in our National Building Code in both Part 6, which is our good practice section of the code, and also Part 9, which is our wood frame construction. And that code goes across Canada. Each of the provinces can either adopt it, and most of them do, and the ones that do adopt it might do slight modifications to it to represent their own sort of geography. But the 214 code for hydronic systems is in the national code, and it now is across Canada. And then we have each of the provinces might have their own design requirements. So the National Building Code takes care of the installation part of it, and then the provinces deal with the design requirements, and then those design requirements are then enforced at a municipal level at the various cities and counties and towns across the country. And it just makes, well, since this has happened, we have seen the number of problems that have been related to radiant and hydronic systems go way down, And so it's been a real nothing but upside and good things that have come about from this sort of nationalization of these codes. So let's look at some of the systems. This project is actually one of the projects that our host and sponsor today worked with. This was a Habitat for Humanity project. All high-performance buildings, and they're using photovoltaics, they're using radiant, and it's a great project because it illustrates that you can do really simple radiant systems, so simple that anybody can put them in, and they're also very affordable. And I just love the whole story around Habitat and what Uponor has been doing with them in terms of these types of systems. So this is your basic run-of-the-mill radiant system, rigid insulation, tube on top, concrete on, and then you finish it up. And you can stain the concrete, you can stamp it, you can leave it bare, you can put other masonry surfaces on top of it or other types. But really, it's a really nice way of doing these systems here. And then there's one of the volunteer crews from Uponor. So I like to see those guys work because oftentimes they're in the office, and maybe I don't know if he's online here now, but it's good to see him with a shovel or a rake in his hand, that's for sure. And then one of the things that we're certainly starting to see more, we actually used to see this a lot back in the 80s, but it's starting to come back now again, and that is that just doing basements or bathrooms or kitchens where you're just doing areas of the house that are traditionally cold because of where they're located or the flooring that they're using. And so basement systems are really nice to do, or the bathroom and also the kitchen. So they don't have to be complicated. They can be really simple. And the nice thing about these smaller systems is that they are simpler and they are certainly more affordable. And the mechanical systems that you connect to them are also really simple. And this is just one of the products that's available there today. So, you could have, as a builder, you could put the tubes in and then offer to the client, maybe you want to, at some later time, add the heating plant. And that's actually what we're looking at here. This is a factory-built, we call them boiler rooms in a box, or substations is another way to refer to them. But essentially, it's a heating plant already there. The electrical boilers there, all the manifold. And it's just an elegant, simple way of just engaging the floor system, just mount it on the wall, connect up the pipes to the manifold, fill it up, and then hit the power to it, and you've got a radiant system that's simple, reliable, and very affordable. And we often spec these on many of the projects that we're working on. So that's pretty much it for the seminar. I really just sort of want to summarize a couple of things here before we open the room up for some questions and answers. And that is, at the end of the day, whatever the stories that revolve around radiant, there's lots of myths, and I'll be happy to answer those myths in the Q&A section. But at the end of the day, it's an enabler. It enables us to achieve energy and exergy efficiency. In other words, because of the low temperatures for heating and the high temperatures for cooling, we can get that mechanical equipment to operate at its peak engineered performance. And that's really what radiant does. Because we're working with fluids, you can use it for just about any energy source that's available, and then preferably, if we can, at a low-grade quality like geo or the ground or thermal solar, but it also can lend itself to other sources as well. The other thing that it offers is this term called thermal efficacy. And what I mean by thermal efficacy is that when you walk into a home that's heated with radiant, particularly if it's done well, you can walk anywhere in that space and there will be less than a half or 1 degree difference. And I've worked on large buildings and small buildings, and we just find that the spaces are so, oops, there's our timer, so we're just about up, that when you walk into these spaces, that they're just incredible how consistent the temperature is throughout the space. And then, of course, the other thing is it enables us to use dedicated ventilation systems. There's no confusion about what the air is supposed to be doing. Air is very good at taking out particulates, what I call the decontamination process. Air is very, very good at dehumidification or humidification. And so it's an excellent medium for addressing the respiratory needs of the occupants. But air-based systems don't perform the same way in terms of thermal comfort. So assigning the thermal comfort, the radiant component, to a radiant-based heating system, and then the ventilation just strictly to the respiratory makes it a really nice combination for a hybrid. And we talked about the VOC masonry, so that we're going to pass that by. The other, of course, benefit is that you're not restricted by what you use in terms of floor area, because we're not having wall-mounted registers or radiators. Everything is in the floor, in the wall, or in the ceiling, so it's hidden. And that just opens up the space for interior designers. Certainly in the heating modes, you can use the radiant system during construction. And then, of course, there's lots of benefits in terms of its safety and the quiet and the creation of really healthy environments is one of the big benefits with radiant heating systems. So that's our presentation for today. And I know we covered a lot of materials. And when you think about, our topics in terms of sustainability and comfort and energy and certainly indoor environmental quality, what makes it difficult but also fascinating is that you're really at the crossroads of a whole bunch of areas of study. It involves physics, and it involves chemistry, and it involves biology, and it involves economics, and it involves our culture and architecture and all of these things. And that's why I love the topic, and I love talking about it, is because when we talk about people and spaces and conditioning people and the options that we have for HVAC, Radiant just sort of sits at that crossroad, and it really becomes sort of the transmission for integrating renewables into high-performance buildings. So thank you very much for your time. Mike, I'll hand it over to you for the Q&A session.
Well, thank you, Robert. I appreciate it. We are starting to have some questions roll in, and like Robert said, I encourage people to submit their questions. I want to start off with a question from Russ. What temperature is the water typically when it leaves the boiler?
Okay, that's a really good question, Russ. So a lot of it depends what that boiler is doing. So let's take the simple system, and let's say that the boiler is strictly just for thermal comfort. In these high-performance buildings, and let's talk about cold and very cold climates where you might be building to an R2000 standard or a let's not go Pascal. Let's go like the pretty good house, right, where you might be dealing with R60 wall ceiling, 40 walls above grade, 20 R20 below grade. You could easily see temperatures leaving the boiler at 100 degrees, 95 degrees. And again, a lot of that depends on the tube spacing and the floor covering. When you get into the terrible buildings or the traditional buildings where you might have really high loads, say in excess of 20 BTUs per hour per square foot, and if they're using, say, a carpeted flooring material, and they're in the joist space, so they're actually fastening the tubes underneath the wood floor, you can easily see water temperatures there of 140 degrees or 150 degrees. So it really emphasizes that there is no one single temperature. It is always project specific, and we see the lower temperatures in the high performance buildings where we're using really conductive floors, more the masonry type floors, and where they're using a tight tube patterns or high density tube pattern, and that's where you get the low temperatures.
Okay.
Next. I hope that answers your question.
Well, if it doesn't, I'm guessing that Russ will send in something additional off of that.
Yeah.
Dave has a question. He wants to know if the emissivity of the floor material does that affect the radiant transfer efficacy?
Yeah, that's a great question. So for those that aren't familiar with the term emissivity, it's what we call a thermal optical property of materials. And when you have high emissivity materials, you tend to talk about materials that have a high texture component to it. Probably the best way is maybe to reverse the understanding when we talk about low emissivity, because everybody's heard about low E windows, for example, or low E products like foil. So low E materials are very, very smooth, like foil or other polished surfaces. So what we're looking for in spaces conditioned with radiant is materials that have a higher emissivity. And fortunately, it's a good thing because most materials of construction actually have emissivities exceeding 0.8 up to, say, 0.95. And let me just explain that scale. So when you have a low E material or a low E product, we tend to be talking things that are in the, say, less than 0.15. And there's actually a definition for low E on foil products. But I define it like in terms of heat transfer for conditioning people. When you get into the really low emissivities, you're talking about 0.15 and lower. And then the mid-range would be up until, say, around 0.15 up to, say, 6 or 7. And then you get into the higher emissivities up into the up to the 0.95. And so his question in terms of does the emissivity of the floor material affect, and it does. So, but you would have to get, you'd have to have a really highly polished surface to have a negative impact on the emissivity or emission of radiant energy from a floor. And but any like concrete surface, tile, slate, terrazzo, wood floors, carpeting, they all have high emissivities. And but I just also want to talk, Dave, to that question because there's one of the myths that we have in the radiant industry is that that tile floors make better radiators than carpeted floors, and of course that's a myth because carpet and tile, by the way, have very similar emissivities, and that's what we're actually interested in terms of the radiant component. Where the effect comes into play is that the carpeted floor has a higher R value. In other words, it's less conductive. And so the result of that is that we have to use higher temperatures in the pipe or closer tube spacings or both. But if we can get both the tile floor and the carpet floor to exactly the same temperature, they will in fact emit almost the same amount of radiant heat. So it's a very good question. And so the answer is yes. And unless you're in a special situation, most floor coverings will have a high emissivity.
Well, I want to add a personal experience to that if I could, Robert, because I once had a fairly lengthy conversation with a gentleman who seemed very well informed on radiant systems. And he was claiming, hey, wood flooring is much better partner for radiant than concrete flooring. And I don't remember all the points that he made. He had quite a few. One was about the cost of the flooring system. But the one that stuck out to me was he was very adamant, you've got such flexibility in changing the ambient temperature. And so I was coming into this, I wanted to get your thoughts on that, and obviously you kind of just spoke to it a little bit. But uh, what's your take on his opinion there? Though you've got the concrete, it absorbs that temperature, and then it's hard to change that.
Yeah, his comment, if I understand what your dialogue was, had to do with maybe thermal lag in terms
Yes.
of we're talking about response time.
Right. Yes.
Yeah. So we need to differentiate between the response of a radiant system in terms of delivering heat to the space and the time that it takes for the floor to actually get up to temperature where it can actually contribute to the conditioning of the occupants in the space. So on the first part, response, radiant is instantaneous. Like those molecules are not the molecules, but the energy waves, the electromagnetic energy waves, they don't need to think about it. It would be, even though we're talking about different wavelengths, the best example would be to turn on a light or stand underneath a heat lamp. This energy that gets released in visible form or in thermal form, well, it turns into a thermal form when we absorb it. It's instantaneous. But getting the system up to temperature, that's what it sounds like you guys were talking about, and that's thermal lag. And that thermal lag is a function of a whole bunch of different things. One of them is tube spacing. The second thing is how deep the tubes are in the floor. The third thing is how thick that slab is. And then the fourth thing has to do with the downward loss and then also the load on the building at the time of startup. So in other words, if you started up a system from scratch,
right.
Under load, obviously, depending on where you are in the country, but let's just take here in Calgary where I'm from, if we were to finish a home, and let's just say, you guys work in Fahrenheit, so let's just say we're working at, around 32 degrees Fahrenheit that we do a startup on a system. Because of the mass of the building, and this applies not just to radiant, but it also applies to air-based systems too. Because of the mass of the building, it's going to take several days for that to come up to temperature from 32 degrees, right? But what happens once you get the system up and running, then depending again on the building and how the floor was constructed and the exterior environmental conditions, the response time on a radiant system can be quite short, like within under an hour or even a half an hour, depending again on the system. Now, how most systems work with the proper controls is that you have what we call weather compensator or indoor-outdoor controller or a reset control. It's three phrases for the same device. This device, you just picture it having a hand outside, and your hand is sensing the outdoor temperature. And then you have your other hand holding the pipe, a supply pipe from the boiler going out to the floor. And what these controls do is that as your one hand feels the temperature drop outside, then the brain says, well, we need to see a temperature increase on the inside. And so it can do that starting at, say, 65 degrees Fahrenheit outdoors. So if it goes from, say, 70 degrees to 65, well, now the brain, the controller, says, well, we're starting to see a drop in the temperature, and therefore we may need to see a rise in the fluid temperature outside. So it's not like, people think, well, we're going to turn on the radiant system, it's going to take forever to do that. That's not actually what happens. What happens in the real world is we use controls to wake the system up, and we wake the system up, whatever, say 65 degrees Fahrenheit outside, and then we start to make everything move and heat the fluid up if the temperature begins to drop. So there's none of this takes all day to heat up stuff. Maybe, yes, on a startup at 32 degrees Fahrenheit it would, but not in general operation. So I'm not sure, Mike, if that answers your question or not, but...
No, it does. I appreciate that.
Yeah.
I wanted to make sure I got back to the audience questions here because they're really why we're here.
Yeah.
Rich has a question about the Uponor boiler in a box. He wants to know, first of all, does it rely on gas fuel? And then if that system is used, what is often paired with that to provide the DHW?
Okay, so that particular product is an electrical-based system and not gas. So it lends itself really well to photovoltaics or anywhere where hydropower is used. So again, it's really important as designers that we match in terms of exergy, going back to exergy, that we match source energy with the load energy. So I'm a huge fan of electrical devices, heat pumps, or in this case an electrical boiler, when that electricity is generated with PV or wind or hydro. But if we have to generate high temperatures for power generation, for again an electric boiler or a heat pump, keep in mind that we're using, again, 3,400 degrees Fahrenheit for 90-degree use. So it's not a real ideal match. So to answer this question, first, it is electric. And so, and then the second part had to do with domestic water. So in this case, if you were using that particular boiler room in the box, I think they call it the Pro panel. Anyways, then you would need an additional heater for your domestic water. If you're using gas-fired, and I'm not aware of any sort of gas-fired product like that electric one. But if it is gas, then of course you can incorporate sidearm heaters into sidearm or indirect fire water heaters to the boiler, and those are good solutions. Although there's certainly we want to be in terms of energy efficiency. One of the challenges with using the sidearm heaters is that during the summer months you are going to be using a boiler to heat domestic water, and depending on the boiler. If it's one of the more modern boilers with a fairly high turn-down ratio, it's not a bad match. But if you're using, a typical or not a typical boiler, but maybe something that's not in the high efficiency range, maybe it doesn't have a turn, maybe it's an on-off gas valve, or even if it's modulating, depending on its size, it may be not the most efficient way of generating domestic water. So to answer the second part of this question, if it is gas, you could use a sidearm heater or an indirect. It's the same phrase. But make sure that if you're going to be doing that you also look at the boiler and its capability to operate at a low load so that you're not full firing a boiler during the summer months just to generate domestic water.
Okay. We've got a couple more questions here. Robert, I want to check and make sure. Are you okay to go a little bit beyond the top of the hour?
Yep, absolutely.
Fantastic. All right, we're going to continue on here with Dave's question. Dave wants to know if you found PEX al PEX to perform greater than straight PEX. I'm not sure exactly what context he's using the word perform in, but I'll kind of let you address his question.
Yeah, I'm not sure. I'll try, Dave, to try to interpret what you're asking for there. In the world of pipe, of course, there's a number of different options available, and the PEX al PEX, for those that may not be familiar, it's actually an aluminum barrier, if you will, that's sandwiched between two layers of PEX. And, both of them, from an engineering point of view, I mean, my main concern is make sure it holds water, keeps water on the inside, and that it meets the requirements, the ASTM and the CSA requirements for us here in Canada. Those are my main components. Or conditions, and then the third thing for me has to do with operating conditions, making sure that the piping that we specify can deal with the temperatures and the pressures, and all of them do. I mean, this audience today is mainly to deal with residential systems, and most residential systems are going to be operating under 30 psi, and if it's a radiant system, typically less than 140 degrees. Well, that combination of temperature and pressure is really it's child's play for any of the pipes that are out there, because they can take much higher temperatures and much higher pressures. So from an engineering point of view, Dave, either pipe, works for us from the operating conditions and the performance characteristics. The PEX-LPEX does have a lower coefficient of expansion, which means that if you heat it up, it's not going to grow as much as, say, the traditional PEX pipe. But it also is very difficult to work with in some other situations. And so, I haven't personally spec'd the PEX pipe for many, many years. We've moved all of our specifications over to the PEX pipe, but it's really just a preference type of thing. Both of them are good.
Okay. Chris would like to know if current code requirements for insulation R values are adequate for radiant floors using poured concrete on grade.
I love that question. So there's no doubt that we have seen, particularly the last 5 years, an awareness of downward loss. And I can tell you that certainly here in Canada, the conflict is not over. And I'll just explain what I mean there, is that when the CSA standard 214 was first published, there was a requirement for a minimum of R5 insulation underneath the slab. And that insulation had to be manufactured insulation. And then when the codes came out for review, through some influence of some certain parties, that R5 was withdrawn for manufactured insulation, was withdrawn from the CSA standard. And the statement that they made was that so long as that the R value or that the soil R value equivalency was R5, that you didn't need manufactured insulation. That flies in the face of everything logical, because one of the comments that supported that R value equivalency had to do with conductivity of soil. And conductivity of soil is a function of not only the soil mix, whether it's a silt or a sand or a clay or a mixture, but it's highly dependent on the moisture content. And the moisture content is highly dependent on both the above grade geology and also the below grade. And so water tables move up and down all the time. They're not just stagnant. And so one of the statements that was in the CSA standard was that so long as that the soil was equivalent to an R5, you could forego the insulation, and which is, as I said, is completely illogical, because water tables move up and down, ergo the soil conductivity moves up and down. And the only way to prevent that from having a negative influence on the operating costs of a radiant system, is to have manufactured insulation. And so in this version of the CSA, it actually got back in again. Now, that's a minimum, and I think it's personally, our standard here in our office is a minimum R10. That's our starting point. If you get into some of these high-performance building programs, where you're starting to talk about, 4 to 6 inches of insulation, I think that's pretty admirable for them to do it. But from our perspective as designers, I don't think we would ever see an application where we would spec anything more than R20. So R10 was our minimum. R20 is for us is more than adequate for a high performance building. So are the current code requirements for insulation adequate? I would say no. I would say we're going to see them go up a little bit. Sort of R5, R10, and I think anybody that's concerned about reducing energy and using the lowest fluid temperatures as possible for heating, that you're going to see that move up into R20. But that'll be a purely voluntary decision, and not something that will be required by code. That's my prediction.
Well, Chris, thanks you for your input on that. He thought, too, that they seemed way too low, and he wanted to mention that he's a mechanical inspector.
Okay, great. Glad. And I see he's got a great last name.
Russ has a question about electric radiant and how it compares to hydronic.
Okay, well, I mean, I guess how you want to compare it. I mean, if in terms of, creating nice temperatures on the floor for conditioning the occupants, or even just to condition the space and to raise the MRT, both systems work. I mean, you're talking about taking a surface that is at a cool temperature and raising that temperature up to some temperature higher than cool. And the standards, ASHRAE Standard 55, it defines what's acceptable in terms of floor temperatures. And that's the ideal floor temperature is around 75 to 77 degrees Fahrenheit. That's where the least amount of people will complain about floor temperatures. And it inches a little bit higher when you get into people wearing bare feet and socks, and then, of course, floor covering comes into play on that. But both systems can achieve the required design temperature. The question becomes one of, again, going back to your source energy and the cost of that energy. And, with certainly the way that natural gas prices are nosediving, we see people switching or moving more towards the gas equipment. So you're talking about boilers as opposed to the electric cables or electric mats. There's no doubt about it that if you're doing really small projects, like let's just say that the client is renovating a home and their main system is an air-based system, but they want to take the chill off the bathroom. There's going to be an argument that you're talking about 100, 200 square feet or something in that area or less. It's hard to make an economic case to put in a boiler or even a water heater when electric mat will do. However, if they're going to renovate that building and they're looking at changing that HVAC system over to a hybrid, where they're going to use the ducts purely just for ventilation, air, maybe humidification, there's actually a strategy for the renovation to improve the indoor environment. Then they're going to be looking at possibly putting in a boiler, and then or some other heating liquid system. Then you can switch over to the hydronic. So it's application based. Both will achieve the same conditioning of the occupants in the building itself. But look at operating costs, your source of your energy, and then look at what the project is. Is it a renovation? Is it a new building? How big is the space? These types of things.
All right, we've got a couple more here, if you don't mind, Robert.
Yeah.
Rich wanted to follow up on the Uponor boiler in a box question. If it is electric, and if we seek to combine it with site solar PV, wouldn't we need a battery bank to handle the amperage draw to provide enough electric energy to heat the water flowing through the box?
Yeah. So what I would do, Rick, on that is I would get a hold of Uponor, who are the manufacturer, and they can provide you the load on that, and then work with your PV supplier to come up with the system, because the boiler itself is going to be just part of the building load. I mean, you're going to have all of the other loads in the building, and so you would need to incorporate that into your PV array. So I'm going to throw that back out to your other resources on the PV side, and then also to the manufacturer of the panel, and they can provide you with the loads. They do have a couple of different models, so they'll match up that particular one for your particular case, and that way you get the facts as opposed to me telling you what you might need.
I like the direction that Russ's question is going. He wants to know what if your fuel source is basically renewable. What if it's solar or hydro or wind?
And so, and I'm not quite understanding what if your fuel source is solar, hydro, or wind? So all of those, what I like about those is that from an exergy point of view, in other words, if you use a solar system with radiant floor heating, and let's just say the solar, either thermal or PV, but let's say it's PV, the nice thing about that is that we're not creating really high temperatures for the purposes of conditioning, the occupants in the space. And the same thing with the hydro and the wind. There's no 3,400 degrees associated with wind power or hydropower or the PV. It's all what we call low quality energy. And that's probably the best way to describe it, is sort of low quality versus high quality. Whenever we take hydrocarbons and we, at a power plant, so if we're using natural gas for a power plant, so that's, going to generate power, and that's going to come into, say, a heat pump or an electric boiler, or you could use hydro to generate that power to come into a heat pump or a boiler. Well, in the case of the gas-generated power, you have all of that high temperature, and unless they're doing co or trigeneration connected to a district energy system, all of that high quality energy is destroyed in the process of heating people. And to me, that just absolutely makes no sense. So, but when you use hydro or wind or PV, because the quality of the energy is low compared to the quality of the energy from the combustion process, it's way more suited. I mean, it's a beautiful marriage between a low temperature system, which needs low quality energy, and a low quality source, which these other renewable systems provide. So I'm not sure that answers this question directly, but those are my comments on that.
Okay. Well, I don't see any more audience questions at the moment, but I had one that I wanted to ask if I could. I've had building scientists tell me that the building envelope called for in the 2012 Energy Code is just about as good as we can do. I mean, there may be incremental improvements there, but for the most part, it's pretty solid. If that is true, do you see the next area of efficiency gains coming from mechanical systems such as radiant?
Certainly is going to, the radiant system certainly enable it. I can't see energy codes on this continent sort of stalling out where they are. It just, again, going back to sustainability, sustainability is for those that maybe they're still in line, it really falls into the branch of philosophy. It's a philosophical discussion. And I can't, humans, we are not definitely acting up towards our intellect. We're a lot smarter than, or we're smart enough to not behave in the way that we're behaving. And so I can't see energy codes stalling out over time at the levels that they're at. There has to be, logic tells us that if we have a fixed non-renewables, the last thing that we should be doing is using high quality energy to condition these spaces. So I do see standard or requirements going up. That will reduce the consumption in terms of the quantity of fuel, and that is augmented with these high performance mechanical systems, of which radiant is. It falls right into that camp because of the low temperatures that are needed. So we don't have a slide here, but I'll describe what I'm talking about. When you go to the ASHRAE handbooks or any of the handbooks on combustion, there's a graph, and it'll say that if you put in a 97% combustion rated, a 97% efficient combustion rated boiler, that 97% only occurs when return temperatures come back through it at around 75 to 80 degrees Fahrenheit. In other words, it's not enough to stick in the 97% efficient boiler and say you have an efficient HVAC system. You have to actually create the conditions for the boiler to operate at those 97% efficiency, and the only way to do that is to get really low temperatures coming back through the boiler. And how you do that is that you use larger heat exchanger areas, which are, it's very fortunate that we have floors to do that with, because it's a very large area. And for those that may not be familiar with heat transfer principles, if you increase the surface area of your heat exchanger, the fluid temperature can go down. If you reduce the surface area of the heat exchanger, the temperature has to go up. That's why when you use baseboards or panel radiators, or you have coils and air handlers, why they operate at high temperatures is because the surface area is so low. But with radiant systems, because we're using really large surface areas, we can get down into these low temperatures, and these low temperatures make these boilers more efficient. So Mike, to answer your question, radiant is definitely part of it. It has to be, in terms of getting the low temperatures through this equipment. So let's just say that, if we can agree that maybe on the continuum of building codes, energy standards, that maybe it's not stalled, but it's slowed down, or the growth rate is maybe not as high as we'd like it to be from a green perspective, that along that continuum, that we have to provide mechanical systems that can extract the most amount of work out of the energy that we put into it. And certainly a radiant is part of that equation.
Okay. Well, Robert, I thank you very much for your time. We did get one more question coming in, but I'm going to have that kind of be addressed privately. So, Russ, if you could put your email address into the Q&A box. It'll come to me, and I'll get your question to Robert. Um, Thank you again, Robert, for sharing your time and your knowledge with us today. We very much appreciate it.
Yeah, my pleasure, Mike. And Mary, thank you very much. And and also to Uponor for making this happen. And, I love doing it. And I hope your audience today got something out of it. So thank you very much.
Now, I also want to let everyone know we will feature another presentation from Uponor next month. On Wednesday, October 16th at 2 p.m. Eastern, we'll revisit the topic of PEX plumbing with Alan Squires. He's going to tell us about the benefits of PEX in multifamily applications. So until next month, take care, everyone.